Okay, sorry about that. Today we're going to kick off milestone 2 of our project. Before we start doing that, few announcements. The makeup exam is due tonight. It's the last time you can take it is about 9 p.m. It's going to be a 3-hour exam, and then you submit after that. If you have an accommodation and I forgot to put it in for the makeup exam and you'd like to take the makeup exam, then send me an email and I'll make sure to do it on the spot. Okay, if you have less than a 60 on exam 1, then you should retake the exam today. All right, so we're going to start off with talking about our project. We have no activity for this session today, so you can just submit today's activity and then tomorrow there's nothing due. There will be an assignment due on Monday that I will post after this. All right, questions about logistics? All right, so let's get our project milestone 2 kicked off. Thank you. So let me get this set up. All right. Awesome. So we're going to start off with the same analogies, the same silly analogies we kind of do. And what you're going to be implementing in milestone 2 of the project today or for the next 2 weeks is the following. You own a movie theater and you have your ticketing booth. So part of what you're going to do is implementing the way people can come in and get tickets from you to go into the movie theater. Okay, so they have tickets, and you're gonna first make sure the tickets are authentic. So did they fake their tickets, for example? Are they using fake ones? You have to make sure that the tickets are authentic and they're still valid. So once they gain admission, they're gonna go into the theater. There are seats in there. There can be several people entering at the same time, and each one of them might choose a different seat, and so on. Okay? Now, you're going to keep track of how many people you have in your movie theater. So this is going to be your database of people in your theater. Okay? Now, also, you're going to hire an employee that every 5 seconds is going to go into theater, make a tally of how many people are there, update several information about those people, including information like, are they actively watching the movie or are they sleeping? Which seat are they in? Did they change their seats? How much time have they been in your theater? Are they overstaying their welcome, for example? So those are examples of what this person whose job is to wake up every 5 seconds, go and look up information about the people in the theater, and then go back to sleep. Do the same again 5 seconds later, and so on and so on. In addition to that, you're going to have something that will let people out as well. And at that same time, you want to make sure that their tickets are still with them and they're still valid before they exit. Okay, so in a sense, you're running an admission control system on processes, and you're also, or on people, and you're also managing the people inside of your movie theater. You're maintaining information. One more thing we're going to do is, if at any point in time a person has been in there for more than, let's say, 30 seconds, if they went into the movie theater and sat there for more than 30 seconds, we're going to kick them off. We're going to kick them outside of the theater. We're also going to be even worse than that, right? What we're going to do is that if they have children with them, we're going to kick them out along with their children. Okay? So that's pretty much what we are going to do in this milestone. Next milestone is you're going to decide the seating plan. For this milestone, we're just going to let someone else take care of the seating plan. Next milestone, you will do the actual planning for the seats. You're going to tell with each person where do they sit and when do they sit. Questions? Okay, so let's actually see how things look like when we're talking about actual stuff. So let's start off with this part, this half. Oops. We're going to start off with a user application. This user application is going to talk to your module through procfs, just like we did in Milestone 1. So we're going to reuse the same stuff we used for Milestone 1. It's going to send one of two commands, either to register with your system, so to go in, it's submitting its ticket, and it's going to send along its ticket, which is its PID. If it wants to leave the theater, it's going to also deregister, and it's going to send along its PID as well. Okay? Your job in your write handler, so this is the write handler because we are writing to procfs. The write handler is going to make sure that the PID that you're telling me is yours is indeed your PID. So if a process tries to come in and register with a fake PID that's not its actual process ID, your module is going to reject that. It's not going to allow it to go in. Okay, so that's the authentication stuff that we're doing. Because we don't want anyone to register on behalf of someone else. That would break things inside of our system. Okay? So once you register a process, then you're going to put things into a database. Okay? This database is in the form of a linked list. And one of the learning objectives of this milestone is to get you to learn how to use the kernel provided data structures. One of those data structures is the linked list. It seems intuitive, but there is some caveats that we're going to have to worry about when using the kernel data structures. But one of the things we will learn in this milestone is to use the kernel data structures. So we have our linked list. Each entry in the linked list is a custom defined process control block. So if you recall from our first few lectures when we started defining processes, each process has its PCB or process control block, and those things are everything that we know about this process and everything that we need to run this process and make sure that it's running correctly. Inside of this PCB, what you need to remember is the following. The Linux TCB, which is nothing but a struct ask struct. So this is the actual process control block for the process. So if I give you a process ID, you're going to go and fetch the actual process control block for that process and maintain a copy of it in your custom control block. So your custom control block is like a wrapper now around the actual task structure, around the actual process control. But in addition to that, you're going to remember the last 5 states that the process was in. So whether is it running? Is it sleeping? Is it sleeping, but there's one more called task uninterruptible, so it's like sleeping and would never wake up. So you have to remember the last 5 states that the process was in. Also, last 5 user timestamps, which is how long has this process been in your system for the last 5 times you checked on it. So remember, we said we have a person that wakes up every 5 seconds, does all of this checking, and then goes out. 5 seconds, does all of this checking, and comes out. So after 25 seconds, you should always see the last 5 timestamps, the last 5 states, and so on. In addition to that, we're going to remember the last 5 CPUs used. So what do we mean by the last 5 CPUs used? Is you might have multiple CPUs in your system. So if you're running a multi-core machine, you have multi-core, you have CPU 0, CPU 1, CPU 2, CPU 3. So you want to remember where did this process run on for the last 5 times. Okay? And there's a bunch of other stuff that probably you will need for your own implementation, but those are the ones that I will require you to remember about each and every process. Questions? Okay. So we are done with the reading part, the writing part, the registration. The reading part is pretty much simple. It's going to allow you, if I read from procfs, I'm going to read the entire database. So I'm going to take everything that's in here, and here, and here, and then dump it back to the user. So anytime I read from the database, I read everything. Okay, so that's similar to what we were doing last time. We were doing integer by integer. This time we're going to be reading custom PCB by custom PCB by custom PCB, and so on and so on. So this is the interface that we're going to deal with when it comes to the actual kernel, or to the actual interaction with the user. 2 things we're going to take care of when we're going to actually doing things in the kernel. So we said we have this person that runs every 5 seconds and then goes back and updates all the values, then goes out 5 seconds later, comes back in, and goes out 5 seconds later, comes back in, and goes out, and so on and so forth. So how do we implement this in the Linux kernel? We're going to use timer interrupts. So we're going to basically very much do the way, similar to the way we set signals, when we set alarm, and then we set the time period, and then at least after this time period, the alarm was raised. We're going to do the alternative or the equivalent to that in the kernel. We're going to set a timer for 5 seconds, and then that timer expires. It tells us that we should update the state of everything. Then we set the timer for another 5 seconds, expires again, we update, set the timer for 5 seconds, expires again, update, so on and so on. Now, the problem here, or the caveat, is that we have the word interrupt. So we refer to this as a software interrupt or a soft IRQ. So IRQ is interrupt request. So if you see the term soft IRQ in your when you're trying to look up some documentation, it refers to a software interrupt that you're doing. Now, the problem is any code that's running in a soft IRQ, in a software interrupt or an interrupt in general, disables other interrupts of its types, of its same type, and prevents preemption. So if I am running from software interrupt and I'm running on CPU 0, then until I finish my computation, no one can yank me off CPU 0 and get in my place. Even if the scheduler wants to kick me out, it will not be able to kick me out. Now, that's good if you want to do things really, really fast. That's bad if you mess up or if you need to run something that goes for long. Because imagine that at every point in time, you have processes that hog one of your CPUs, or you have jobs that hog one of your CPUs. If one of those mess up and gets caught into an infinite loop, pretty much your machine is done, right? You can't do anything. You can't take it off of the CPU and put something else in its place. It's just going to keep spinning on the CPU infinitely. So the way we handle this is we're going to try to minimize the work we do in the interrupt, and we will use a concept called work queues. So work queues, you can think of them as functions or even yet threads that run in the kernel. So these eventually will come or will become kernel threads. So once I put a function on the work queue, we refer to those as works. Once I put a work on the work queue, the kernel will take care of scheduling that work to run in a kernel thread. And probably sometime very soon after I put it on the queue. Okay? Now, work queues run in kernel threads, and they don't suffer from, they do not suffer from the same problems that software interrupts suffer from. So in a work queue, I can loop forever, the scheduler can kick me out, I can go to sleep, and the scheduler can swap me out, and so on and so forth. So I can do a whole bunch of things that it was not possible for me to do in a software interrupt. So the way we're going to solve this issue is the following. Our software interrupt is actually not going to do any work. It's only going to put a work on the work queue and then go out. Then once the work on the work queue takes place, it will do the updates. So the only one that's going to update things is the work on the work queue, not the software interrupt. This way, we make sure that our software interrupt runs as little as possible, maybe 1 or 2 lines of code at most, and then the work queue is the one that does the work in the work queue is the one that does most of the work for us. So what the work is going to do is going to come in here. It's going to read the kernel task struct, which is the actual PCB. It's going to use the information inside of it to calculate and fill out these numbers. Okay? Questions? Okay. 2 more things we want to talk about as well. These are the following, the last 2 things. We said that we want to kill a process, terminate a process, if it takes greater than 30 seconds, for example. So we must allow the timer or we must allow the work queue to actually kill processes. And if that process has children, it must first kill the children and then kill that process as well. So we must provide support for us to be able to do that only if 30 seconds have passed since the program has started. Okay? And the last thing we want to care about is do you see a race condition in this case in our project? Yep. Yeah, exactly. So these two, they run asynchronously. So what it means is that they can run at any point in time. So what if the 5 seconds expired at the same time I'm trying to write to the database? So write, clear this up a little bit. Write is happening at the same time the timer has expired. This is clearly a recipe for disaster, right? Because they're both trying to update things at the same time. We have no idea what's the output of that thing is going to be. So that's why we're going to need finally to do synchronization in the kernel. And we're going to use, there's several types. There's a mutex, there's semaphores, there's a thing called spin locks. And part of the challenge in this project is figuring out which one of these you want to use at which point and from which context. Like we said, the timer interrupt runs in interrupt context, right? So it cannot be preempted. So it cannot sleep. So this automatically makes semaphores and mutices out of the question, right? It leaves spin locks, but the work queue can sleep. So the work queue can use semaphores and mutices. So it's up to you to figure out exactly which one of those constructs you're going to use. And I have a bunch of description about each in your document, and I link to the recipe handbook for figuring those out. So you're not going to just bang your head against the wall to figure them out. I've given you the instructions. You just have to apply them for different contexts that you have. Yeah?
You said we couldn't use the semaphores or anything.
Yeah. So no, what I said is if you're locking from the timer, then you can't use semaphores and mutices. Because semaphore and mutices cause the running thread or process to sleep, and we're not allowed to sleep when we are in the timer. Now, if you choose to lock from the work queue, then you can use those semaphores and mutices. So it depends on where you're locking from. Okay, questions, other questions? All right, so I wanted to show you how the outcome of this is going to look like. So let me try and get this running and switch machines. Okay, share screen. Okay. Okay. So is this visible, or should I make it larger? Good on the back? Okay. So let's go into the project. Okay. So clean. Let's make. Okay. So the first thing we're going to do is I'm going to show you what things to expect when you're completed this project. So let's insert our project. So you can see in the message that we're just going to print that the module is initialized. Same way we did for milestone 1. I wrote a user application. But before we do that, the first thing I want to show you is what happens if I try to register as a fake process. Right? We said that you should always make sure that if I pass you a PID, that PID actually belongs to you and is not someone else. So let's try to do this. If I do register 1111 to proc status. So what I'm gonna get is an error message from my module telling me that this operation is not permitted. Register as someone you are not. Your PID must match the PID that you're registering with. And 1111 is not the PID for Echo. That's why it wasn't allowing me to register. Okay? So let's take a look at the IO app, user app.c. And what the user app is doing, it's first gonna fork into a child. So it's gonna do the same thing from a child and a parent. It's gonna try to read from proc CSSE 332 status, and it's gonna try to open it first, write its own PID into it to register. So it sends R, comma, space, the PID. And if it fails, it's going to print and exit. Otherwise, it's going to try to read from the procfs entry, and then it's just going to go into an infinite loop after that. Okay, so it's just going to go into an infinite loop. So, and the same thing happens to the child. The child is going to go in, it's going to read, it's going to register, it's going to write, it's going to exit, and so on. So that's pretty much what's going to happen. Okay, so let's check out what happens if I run this. So you can see that my application is running forever. After it registered, it saw that there was one process. Its name is user app. We haven't updated anything yet. We can't see the status yet, but we know that it has one child, which has PID 2099. So let's send this to the background and now try to read from procfs. Oops, I wasn't fast enough. So let's do that again. So indeed, what happened after the first read is the child now registered. So now you can see two applications. First one is 2184. It's called user app. Second one is 2186, which is a child of 2184. It's also called user. Now, if I check again, I can see that I have a bunch of timestamps that have been registered. 4 CPU values have been registered now. So if I read again, it was killed. So you can see that this one was running. This one was interruptible, which means it was sleeping. So things are happening in the scheduler. It's changing the state, and we can see which one of those are happening and which CPU are they running. And we're updating those regularly. Now, if you look at this point in time, you're going to see that the process was killed. I did not kill it. What happened is that the kernel module, once it has run above 30 seconds, it killed that process, which was what we actually want in this case. So the way you want to test your system, because we have synchronization, you want to maximize the chances that if you have a race condition, that race condition is going to be exercised. The way to do that is I'm going to run several instances of my user. But I want to run those in the background. I don't want all of them to run sequentially. So if you want to run a process in the background, you just have to add the and character at the end of the command. So if I want to run user app in the background, I just say /user app and. And I'm going to run, let's say, 3 instances of it. OK, so let's take a look at. So you're going to see that we have 1, 2, 3, 4, 5, 6 processes in total registered in our system, right? And you can see that a bunch of them are running, a bunch of them are interruptible, are sleeping, and so on and so on. OK, so let's give this a little bit more time. And there we go. Killed, killed, and killed. And if I try to read now, there's nothing left. So all of my processes have been killed because they did not finish in 30 seconds, which is all of the quote I'm allocating for. Questions? OK, so now we're going to go back here and talk a little bit about the actual implementation before I let you go. All right, so. Share again. All right, awesome. So what I want to spend the rest of the 10 minutes we have talking about is the linked list. And how do we use linked lists in the Linux kernel? So the way things are defined in the Linux kernel is that you have a struct called listhead. And then in it, there's just nothing but a next and a previous. So in a sense, this is a doubly linked list. You have a pointer to your next and a pointer to the previous pointer. OK? So if you want to create a linked list, you're going to create a list of list heads. But now the problem comes in is that, well, like I'm creating a linked list of list heads. What I want is a linked list of PCBs, right? We want to create a linked list of, excuse me, process IDs or process control blocks. And what we're creating is a linked list of list heads. So how do we solve this problem? Luckily, the kernel provides us with a rich set of constructs that allow us to do that. The way we define things is that we have a kernel linked list begins with a sentinel. So this means that it's a list element without data. So the head of the list always does not contain any data. It's just a list head. And it points to its next value, and it points to its previous value. So this is the tail, this is the head. However, the tail, excuse me, is not a sentinel. So the tail contains, so it means that it contains data. Only the head does not contain data. And the way it's defined is you're going to put this list head, so this is a list head, struct list head. You're going to put that inside of your PCB. So this is our, it's called the CSSE 332 PCB. Inside of this structure, you're going to have a struct list head. Now, when you want to iterate over your, so same thing is going to happen here. So this is a list head, and then you're going to have, this is inside of a CSSE 332 PCB, and so on. So, however, if I start from the head and I start reading forward, I'm only reading the list heads. So how do we get to the container that contains the list head? Luckily, the kernel has us covered, and they provide a macro called list entry. So in list entry, I pass my list head. So the first parameter is going to be a struct list head star. The second parameter is going to be the size or the type that I'm reading. So it's going to be struct CSSE 332 PCB. The last parameter is the name of the element in the structure. So if my element is called list, for example, and I pass list in here. And now if I put this guy, here, and what I get as a return is the full PCB. So how does the kernel do this? It's going to do some pointer arithmetic because it knows where the list head is. It's going to calculate an offset, and it's going to give you the pointer to the actual container. So you don't have to worry about how that works. But to go from a list head to the structure that contains the list head, you can use the list entry macro, and that will give you exactly what you want. So you start from your head, you start traversing list head entries, then for each one, you call list entry, and you get the actual PCB entries. So that's how the normal progression of using kernel linked lists work. Questions? Okay. So where you find all of these functions and how to use them is in the file linux/list.h. So I highly recommend that when you're coding, you take a look at this here. There's a lot of very useful macros that are defined for you inside of this file. Okay? So one of those is, for example, list for each, which goes over every single element in your linked list. It just does a traversal of your linked list. Another useful one is list for each entry, which is basically is going to do the iteration over PCBs rather than list heads. And one of the most useful ones is list for each safe. So if you recall from your 230 days or 220, if you are using an iterator in a loop and you delete the iterator, what happens? Yeah. Can you say that again? Say it. I couldn't hear. Yes, you got the concurrent modification code. Thank you. You're going to get an error telling you that there is an exception. You're trying to modify an iterator, remove an iterator while you're iterating, right? So that's not allowed. The same thing is going to happen here. If you call list for each and you delete an element from the list inside of list for each, now it's not as nice as Java. It's not going to tell you anything. It's just going to crash. And it might break your VM. So you have to be careful. If you want to avoid that, you can use list for each safe, and that gives you the actual answer you're looking for. Okay? So where do you find those files, and how do you find them? I'm just going to point you to this very useful website. It's called Elixir. In there, if you type, I want to figure out where list for each is. It's going to tell you that list for each is defined as a macro in list.h. You go in to list.h, and it takes you exactly where you want to be. So it tells you that list for each, the macro list for each, is nothing but a for loop that goes from head arrow next to all the way until it recurses through, or it traverses all of the entries. So if you want to see, for example, list entry, so let's click on it. It's going to take us to the definition, which is here. So it's going to call something called container off, and that container off is the one that's going to do the calculations that we saw previously. So I highly recommend that you take a look at this file. There's a big number of very useful functions. Okay. Questions about the linked list? Okay. One more implementation issue I wanted to talk about before I let you go. I'm just going to clean up here a little bit. Okay. So you notice now, in the first case, in the previous milestone, when we called read, we were actually just reading an integer from our list, right? From our array of 10 integers. And then we used the offset pointer, or LOF underscore T star off B. We used that to figure out where do we want to read from in the list, right? So how can we do that now that we have to read entire structures and not we're just indexing into an array, right? So how do we make that happen? Should we, like, if I call with off pointer is 2, I iterate through the list twice and then return. I call with off p3, I iterate again. That's very inefficient, right? So we want to do something that's a little bit smarter. So there are 3 ways to implement this. You're free to pick out each one of them. I will tell you what my favorite is, what the least one that's error prone is, and then you're gonna pick the one that works for you. Implementation 1 is use off p as a list head pointer. So what do we mean by that? I'm gonna use an integer to hold the value of a pointer. Okay? So in a sense, I'm gonna cast an integer, I'm gonna cast a pointer into an integer, and then cast that pointer back, or cast that integer back into a pointer. So I do something like this. I have a list head star. I cast into an integer, and I put that in off B, and then I cast back into a list head star. So this is what's going to cause the least amount of code rewrite from milestone 1. But this is a very dangerous idea if you want to pursue it, because you're casting a pointer into an integer, and bad things can happen if someone else touches that pointer. You're going to have a big bunch of problems. So I would not recommend doing this. The second idea, or the second approach, is the first parameter of your read callback was called a struct file fptr, which is basically the file that you're reading from, the virtual file, the procfs virtual file that you're reading. This file has an entry called file p arrow private data. So private data is a void star pointer that you can use to do anything you want. The first time read is called, private data is null. Second time, if you set it in the first read, it's gonna persist to the second read. If you change it in the second read, it's gonna persist to the third read, and so on and so forth. So you can use that the same way we were using off p, but instead of being an integer pointer, now you have a void pointer that you can use and persist across the reading session. So this requires a little bit of code rewrite because you're going to maintain things manually. So this requires rewrite plus manual maintenance. Option 3 is we're going to use sequential files. So sequential files are simply files that I read in a sequence. So I read first entry of linked list, second entry of linked list, third entry of linked list, and so on and so on. Sequential files are designed with this process in mind, with this idea of reading things in a sequential manner, right? I gave you the skeleton code for it, and here's the benefits of it. Or the downside is that it's going to require code rewrite. The benefits, so this is minus plus, it's easy, not ugly, and no maintenance. So what do I mean by no maintenance? That there are built-in functions that allow you to read a linked list through a sequential file. All you have to do is call those functions and you're done. So in the code, skeleton code that I give you, you have to write 3 lines and then a code to actually just print stuff to the user, right? So that's what I recommend. This is very stable. It minimizes the errors that you're going to do, especially memory corruptions. But it's totally up to you. If you don't want to rewrite things, you can use both method 1 or method 2. Okay, questions? All right, so that's all I had for today. We have an assignment due on Monday. I haven't posted that one yet. I will post that today. We don't have an activity due tomorrow. So after you submitted today's activity, you're done for the week. Enjoy your breaks, and I will see you on Monday.